So, welcome to Module 44. Today we're going to talk about ordinary least squares geometry and assumptions. This is going to be a bit more math heavy than some of the previous modules. We're still going to have lots of code, and we're going to introduce some new simple APIs that you can use, and we're going to explore further in subsequent modules. But this is also sort of just a background that will help us understand the processes that we'll need later. Still extremely important. By the end of this module, you ought to be able to explain linear regression as projecting a target vector, something you're trying to predict, into a feature space. You'll be able to write down the matrix form y equals big X times beta plus epsilon, and interpret beta and epsilon, or at least beta. You'll be able to derive, at least to some extent, something called normal equations, and see why residuals are orthogonal. This is a bit of an aside, but it helps as a framework. You'll be able to diagnose basic violations of OLS using residual plots in context. And you'll be able to connect these assumptions to honest evaluation and responsible decisions. This is always the theme of this course. It's super important when you're doing any work in data science to always be honest and responsible. So let's just kind of figure out what we're talking about in the first place. What is regression? So regression is basically the idea that we want to create a model, some kind of representation that we can use to predict a numeric outcome y. A model can mean many things and have many purposes. Sometimes one can consider it as just being a tool that we use, just to make predictions on things. Sometimes we care about the model in terms of the representation of the world. And those are slightly different uses of a model. One is very functional and one is somewhat more explanatory. But both of those concepts are intimately related. And I think generally the more you want to improve the predictive power of a model, the more you need to explain it or be able to understand its internal workings. And the more you understand its internal workings, the better you can perform predictions. So the kinds of predictions we might want to produce are predicting disease progression from clinical measurements, perhaps estimating daily air pollution given just traffic and weather. You might see on apps, the pollution level meter, and the input to such a model would be like the traffic that you can obtain from various sources, weather you can obtain from other sources, and those two bits of information combined ought to be able to predict air pollution. You might be able to have some weight and horsepower information on vehicles, and you can use that to predict fuel efficiency. We're actually going to see examples of some of these shortly in the worked examples. So linear regression, so the key thing here is linear, basically predicts these values y, these outputs y, as a linear combination of features x sub 1, x sub 2, so on and so on, all the way up to x sub p. Sometimes x sub p is written x sub d, whereas d stands for dimensions, but this is, I try to adopt the conventions of whichever niche we're talking about. You can think of it in this way. So some prediction y, like y hat for the prediction, equals the, some initial scalar b sub 0. We can call this the bias. This is like the default extra amount we provide to the prediction. But then we have basically a sum of all of our input variables, x sub I, for whatever I is. And each of those is multiplied by some number. We call it beta sub I. And all of these things combined gives us our prediction. And what we have here, we can't really choose what data we're given, the x's, but we can choose the coefficients beta to make the predictions as close as possible to the observed y on the training data. Okay, so we have a lot of data, a lot of instances of x's and y's we'll talk about in a moment, and we have at our disposal the ability to modify beta to maximize this closeness or to minimize the distances. In fact, this is exactly what close means. There's many different ways you can measure closeness. We've seen a couple of measures of closeness very recently in the previous modules, actually, when we talked about k-nearest neighbors. In k-nearest neighbors, we had an option of the L1 distance, which is Manhattan distance or the city block distance. We had the L2 distance, which is the squared distances. And that's basically what we're going to be taking here, the least squares. We want to minimize, out of all of our data points, the sum of the squared errors that we produce on making predictions of this type. So let's try to define this a little bit. We can look at the matrix form of this equation. So now, just to specify things, we're going to have n data points, and each of these data points will have p input features, and then they'll have an output that we're trying to predict. So y is our outputs. If we have n data points, we're going to have n outcomes that we're trying to predict. So y, it can be thought of as like a very long, ideally very long vector of numbers. And big X is a big matrix. Normally capital letters refer to matrices. And big X is a n by p plus 1, we call it design matrix. It's basically a matrix of our input features. So again, the number of rows, like every row corresponds to an input datum, an input data point. And the columns basically correspond with the input variables we have. Going back just a second here, we have x sub 1, x sub 2, all the way up to x sub p. We also have like an invisible x over here, which kind of doesn't exist. It's like an invisible x to the power of 0, basically. This gives us our bias term, so we need to consider that, which is our first column of 1s here, right? These are variables that aren't going to be, like this 1 is multiplied by beta sub 0 in this slide. So here, x sub ij means we're dealing with data point I, that's row I, and we're looking at feature j. So x sub 2, 1 here means the second data point's first input feature. And we're also going to have these betas. We're going to have p plus 1 beta values, each one of which we're going to have to learn, and then we multiply those by these rows. So the idea here is we have an idea of reality. Reality, we assume, follows this linear combination. So we have a big matrix X of all of these data points. All of these data points ought to be multiplied by this vector beta. And there's always some noise in the real world. I think we talked about this in a lot of the earlier modules. The world generates noise. That kind of constant noise is called epsilon here. So again, x times beta is going to be the model's predictions, and then we're going to always have a certain amount of error. This is what we call residuals or noise. So this is the objective. This is when we're getting into like how we actually do the predictions. This is going to be very important. We have like an infinite number of ways we could set beta here in this equation to try to fit it to reality. But which one is the best value of beta? Which are our best coefficients or weights that minimize the error of our predictions? Well, we can define it this way. So if we look at the squared difference between all of our desired outcomes y, like all the true values that are produced by the real world, by this formula down here. And we just compare that with the predictions made by our model. Our model predicts x times beta for some values of beta. Then we're going to be a little bit off. We're going to have a prediction that's a little bit above or below the true value of y. On the continuum of y, again, this is where we're making predictions into the real valued space. So sometimes you can over-predict, sometimes you can under-predict. And just to sort of deal with, or not have to deal with the positives and negatives, we take the square differences. So this is our good old 2 norm. And all we want to do is, out of all the available betas, we choose the one that minimizes this squared difference. So some particular value of beta, which gives us the smallest possible difference between true values y and the predictions x times beta. And that's the beta that we like the best. That's the one that's the best fit for our model. We call that beta hat. So again, this we saw this previously, but this represents the Euclidean norm. And you can write out like y minus x beta squared in this form. This is a bit of linear algebra that you probably know already. There's nothing really fancy going on here. This is just the square of the terms inside of this norm. This t is not to the power of t. This indicates the transpose. Remember, these are like y is a vector. the matrix X times beta is going to give you a vector of predictions. So a vector minus a vector is a vector, and to be able to multiply them together in a way that gives you a scalar, you have to just take the transpose of one. So take the row of one times the column of the other, you get your scalar, which is your distance. So this ordinary least squares objective, or goal, gives like the one best fitting vector of predictions among all of the other linear combinations of the columns. And the key idea is that this is maybe getting a little bit under the hood a little bit, but the columns of X, the different variables we have at our disposal, span a subspace of the n-dimensional real-valued Euclidean space. Okay, and OLS finds the closest point in that subspace to the actual data vector y. I think, well, soon enough I'll show you a visualization of this if it's not clear. We're just going to define it a bit more, just conceptually. This is a little bit of an aside. If I could put this microscope as like somewhat translucent, I would, because not everything here is totally skippable. But I'm going to try to walk over this in broad strokes. Real values times n, this is to the power of n, this is an n-dimensional space of real values. This is a big space, and in all this space we have points, which are length n vectors, if you have n data points. And you have target values. There's one particular number per data point, which forms a single vector y in this space. So again, we have n data points, y is an n-dimensional vector, which exists in this n-dimensional space. It's a point in the space. And all of our features give us columns of X, and every column is also a length n vector. Just imagine this, I'll go back here for a second. Each of these columns of this big matrix X is an n-dimensional vector. So if we look at all of the vectors you can get by taking linear combinations of the columns of X, so like X times something beta, then all of these live together in a flat sheet or hyperplane inside of this space, and we call this the column space of X. If that's too complicated, you can just keep things simple. If you have just one value, like if you only have one input value, so P is 1, you have only X sub 1 and that's it, then this hyperplane is just a line. Like you have one value Y, you have X, and so you draw a line in this space. If you have two inputs, then this forms a plane, and so on. We're going to see a plane in the very next slide to make that clear. So we're going to see this example in a second. Generally, if all of the features are independent, which we normally assume that they are, this is a P+1 dimensional flat surface. Okay, so a plane exists in 3 dimensions, and P is 2 in this example. So ordinary least squares basically says among all of these possible predictions on this sheet, pick the one that is closest to the truth, in a straight line, which is basically relying on the Euclidean distances because we're in a Euclidean space. So draw the closest, of all the possible predictions you can make, which is represented as this hyperplane. You have a particular point, which is the point representing all of our all the true values we're trying to predict y, and somewhere there's a prediction that is as close as possible, a vector representing all of the predictions that is closest to the true predictions of the things we want to predict y. Okay. If we choose a value of beta hat, which is closest, which minimizes the distance between the true values y and the predictions x times beta, then this is basically a projection of y onto the column space of X, onto this hyperplane, which we're defining as the space of all possible predictions, X times beta. And then this vector, this line connecting the true values y to the predictions X times beta, this is called the residual. And it's going to be perpendicular to the sheet. So, a lot of people like looking at things visually, so here's what I'm talking about. We have a vector of representing all of the true values we're trying to predict, which is just point y over here, and then we have this hyperplane, which is just a plane in this 3-dimensional space, which is this kind of shaded region. This represents all of the possible predictions we can make for our n data points. This is the blue sheet over here, So you can imagine like a vector somewhere here is going to be like a vector in this hyperplane basically refers to a particular setting of beta. But there's a particular setting of beta that gives us this point down here, which is x times beta hat, which is our best possible value of beta. And it's the best because this purple line here is called this residual, r, which I just defined a moment ago. This is the shortest distance from the true values y to all of the possible predictions, which is this plane over here. I don't need to go into the proof too much, I think, about this, but the shortest distance between this point and the plane is the straight line to the plane, which is orthogonal to the plane. So down here, there's a little bit of a right angle. Okay, that's basically it. So this is again relying on old linear algebra that you must have seen before. So I'm not going to spend too much time on it. To a large extent, this is also based on what we saw previously when we talked about the dot product. A lot of the same kind of intuitions about triangles in the space and right angle triangles in the space specifically come into play here. So we have lots of possible like straight line predictions on this plane over here, but the one that is the closest to the true values y is this point down here, x times beta hat. So hope that makes sense. We've already seen projections, so we know how this works. So this is what we want. We want to choose a value of beta such that our predictions are right at that point. How do we do that? With some minor amount of work. So we want to choose beta to minimize the square difference. The true value is y minus our predictions all squared. We call this the loss, L, and L is parameterized by beta. Like we're given y, we're given all of our inputs x. The only thing we can change is beta. So beta is our argument to this loss function. And we mentioned a moment ago that this square is just the product of y minus x beta, with itself. And to do that, you have to have this transpose. Now, you may not remember this, but when you have a squared function, these kinds of functions are called quadratics. And quadratics have this interesting property that they kind of follow this like bowl shape, where if you change beta, then the value you're predicting, this square, is like concave downwards like this. And that's very useful for us because that tells us by definition that the lowest point in this bowl, right, this curve, which represents our loss, our error. Remember, the loss is our error, L is our error. So we want to minimize the error. We want to basically go down this bowl to its lowest point. And we know that there's exactly one of them because this is a quadratic function. What is that lowest point? Well, it's the point in which the derivative, as you go down this bowl, becomes 0, right? So here it's highly negative because we're going down. It's going down in a pretty steep fashion. But gradually, as we get closer and closer to this optimum point, the derivative, the slope reduces somewhat. It's still negative. We're still going down, but it's not going down as fast. And at some point, we cross this point right here, indicated by this blue dot, and then the slope, the derivative here, becomes positive, and we start going up this curve, right? Higher and higher. So there's one exact point here where the derivative, going from left to right, goes from being negative to being positive. That's when this derivative is 0. And that's the point where, that's the setting of beta, which gives us the lowest loss, okay? So you can see that in this graph. There's some proofs behind that, which is beyond the scope of this class. I'm relying somewhat on your previous experience with these topics. So again, the loss function, L of beta, the error function, is a smooth quadratic bowl, and its unique minimum is exactly where I just mentioned. So solving the derivative with regards to beta and setting it to 0, so finding the derivative of this curve, which is this little kind of nifty thing here, nabla, according to beta, of our loss function, setting it to 0, which is when the derivative is horizontal here, will give us the best value of beta once you solve for beta. So let's go ahead and do that. I'm not going to ask you, I want you to understand what I'm doing here. So this image should hopefully get the point across, and that's the most important thing practically for what we're doing. I'm not going to ask you to do very much differentiation on quizzes and exams, but I want to provide it for you anyway because it's always important not to be scared to look under the hood a little bit. So here is our derivative of this function. So starting with this function, well, maybe starting here. So like, speaking kind of loosely, the loss function derived with regards to beta is going to be this entire thing. This is a function of beta raised to the second power. And we know to do differentiations with that scenario, what we have to do is take the power and bring it down. So it's going to be 2 times just the function times the derivative of this function with regards to beta. So that's what's happening here. We kind of bring down the 2 from up here, which is what we see over here. Then we multiply, like this function here is y minus x beta, which is here. So it's 2 times y minus x beta. And then we take y minus x beta and differentiate that with regards to beta. That's 2 terms. There's no beta in the first term y, so that just becomes 0. It becomes nothing. Minus x times beta, the derivative of that. Well, that's just the derivative of, like, we take the 1 down from the beta, bring it down in front, beta sub 0, beta to the power of 0. We're left over with x. And the derivative of this entire parenthetical operation is just minus x, which is where this minus and this x comes from. So I could have written this out in a different way. It could have been 2 times y minus x times beta times minus x, but I just moved things around just for simplicity here. So this is the derivative of our loss function. I want to set it to 0 because that's the point where beta will be minimize this function. And also expand things. So I can get, setting this equal to 0, I can divide both sides by minus 2. That'll basically get rid of this minus 2, and I'm left with x transpose times y times x transpose times x times beta equals 0. So the minus 2 just disappears because I've divided both sides of this equation by minus 2. And then I can rearrange a little bit. So I can move things around. I can move this x transpose y to the other side, multiply both sides by minus 1. That gives me this equality. This is called the normal equations. Now, if x transpose times x is invertible, which means I can divide both sides of this equation essentially by x transpose x, this gives me beta equals everything over here. And I'm done. So I can solve this analytically. I'm given x. I just have to take this transpose, multiply it by itself, invert it, multiply it by x transpose again, and multiply that by y, all of which I'm given, and I can find the best possible value of beta just by using this function. So I put a box around it because it's important. So from the normal equations, which we just solved, we have this form. This is a bit of a condition. So the residual r, that vector that connects y to the best possible prediction, this product is just going to be equal to 0. This might rely too much on some of your intuition about linear algebra, but basically what this is saying is every column of x in our input matrix is going to be orthogonal to the residual vector, which points from the vector of all of our possible predictions to the vector of true values y. So in other words, if you've chosen the OLS line plane, like the hyperplane, there's no remaining linear pattern between any of the residuals and any feature of x. So looking straight down at the hyperplane from the point of view of the vector y, there's not going to be any influence on any of the features x. So this is a fancy way of saying, what we kind of looked at a moment ago, which is that this residual vector here is going to be at a right angle to our plane of predictions. So maybe some examples to maybe just help clarify what we're talking about. We have 2 examples. So the first one has to do with diabetes progression in 1 dimension. So keeping things very simple. We have a data set. It's a classical clinical data set. Every row will represent a patient. We have many features. We have BMI, blood pressure, etc. and we have a disease progression score, just a value that we were trying to estimate how far along is the patient in terms of their progression of the disease. But we're going to start with a simple one-dimensional regression. We're going to predict this target using only BMI. So here's this bit of code. This data set comes from sklearn data sets. Specifically, it's called low diabetes. And we're going to use linear regression. So here's another introduction. This is the library is sklearn. The subcomponent is linear model, and in that there's this class called linear regression. So at first, all we're going to do is just load the diabetes data set as a data frame and store it in dia-B for diabetes. We're going to copy some of it, and then we're going to rename some columns. So target is just going to be called progression. And then I just want to see, again, do a quick sanity check. I'm just going to take the head of some BMIs and some progressions. So patient 0 has a BMI of 0.06, and their progression in this database is 151, and so on. So here we can visualize the relationship between our inputs BMI and the value we want to predict, which is the disease progression. And every dot over here represents a patient. Nothing much fancy is here. I'm just showing another scatter plot. So the first thing here to think about, just qualitatively, if I'm going to try to fit a straight line to this data, if I want to do linear regression, is it even plausible? Like, does this data look like it falls on a straight line? We saw some examples previously during the visualization modules about this kind of question. I'll leave it up to you to answer that question. And also, like, relatedly, if there's any nonlinear pattern here. And again, we talked about nonlinear patterns in 2 dimensions in previous modules. So I want you to answer this on your own, but for the sake of the slide deck and for the example, we're going to assume that we can fit a straight line here, or at least we're going to try. So here's where we actually call the function. So linear regression is going to be our model. Here we're just initializing it. Again, I mentioned this before. A lot of our functions, we saw K and N in the previous modules, K nearest neighbors. It had its own fit function, which implemented the fit function in its own way. Linear regression, essentially, will choose the values of beta, which we've been spending some time talking about, such that x times beta will give us the best possible predictions to y, according to least squares distances. And then we'll just do some model predictions and then output some information about our model. So the intercept, or the bias term, is what we called beta sub 0 previously. And we only have one coefficient because we only have one input variable, BMI. So that's beta sub 1, and I'm just going to tell you what that is here. So that's like the intercept, or beta sub 0, is 152. That's sort of like a baseline bias for our model. And then the slope of our model, we can call it slope because it's a nice 2-dimensional line. It's beta sub 1, and that's 949. I'm not sure why I included all of this here. But there's a lot more information here available to us than just BMI. So you have age, sex, BP, and so on. I wanted to just mention here, I guess, like the main thing is progression and the prediction. So progression is like the Y values we're trying to predict, but then pred is what we actually predict. This is what X times beta actually gives us. So you can see that they're quite a bit off, at least, subjectively. Again, always want to visualize things. You want to look at your results from every angle, so to speak, possible, from any kind of tool you can throw at it. So here's just the visualization of our model. Here's our disease progression and our slope. And yeah, so just want to make sure something, I always get to double check. So the intercept here is 152.13, and you can see at 0 over here, the intercept is indeed around 150 something. Okay, so that's our intercept. This is our fit. So how much, you can ask some questions now. How much progression score changes per unit increase in standard BMI? So looking at like the linear relationship between BMI and disease progression, you can get from basically looking at the slope. Is the predicted progression when BMI is 0 realistic? Well, we just looked at that a moment ago, and maybe. It's kind of hard to tell looking at these images, but so far nothing extraordinarily awful leaps out at us. We can look at the residuals. So basically I'm just kind of rotating the space. looking at the residuals or the errors according to each of our BMIs here. So this is the progression, like the actual values y minus the prediction for each of our BMI values. You can see that this cloud is pretty wide. So it's something to look at now in this graph is, are these residuals more or less centered around 0, as they should be? You should have roughly the same amount of positive and negative examples. And that seems to be, again, very superficially somewhat the case. There's not much of a shift of all of our cloud of data points above or below this line, 0, in terms of our residuals. And there's no U-shape, there's no obvious nonlinear relationship here that's unaccounted for, which is what we want. So yeah, this is basically like a visual version of is there a remaining pattern in our residuals that's not accounted for nonlinearly, and that doesn't seem to be the case. This is the distortion, so we can look at, we can count up all of these differences between these points and 0, and some of them are positive, some are negative. We just count them all up, put them into a histogram, look at the overall distribution, and we get this. This is the count of the residuals in each of these little bins here. It more or less looks Gaussian. It's more or less centered around 0, which I mentioned a moment ago is what we want. And there's no big spikes or anything crazy going on, so I'm kind of comfortable with this distribution of residuals. It's more or less, it appears, at least visually, to be somewhat normal. So this kind of analysis might matter more if we want to dig into statistical significance testing. We talked about p-values in a previous module. If we want to compute confidence intervals, again, we're kind of doing a little bit of this somewhat superficially, but you can go deeper into an analysis of these distributions to characterize your fit, how well your model fits the observed data. So in practice, ordinary least squares is used when some of these conditions are roughly true. There's a linear relationship between what you're trying to predict and the input variables, and the input variables all can add together in a linear fashion. You can apply it when the residuals are going to be mostly independent of each other. There's no obvious dependency relationship between one residual and another. So every prediction is going to be somewhat independent of the others. This is often something people just assume without checking. So often you can do it too, but it's worth remembering that you can check. Homoscedasticity is referring to constant variance. So in some situations, variance can change over an interval over time. So here the residual variance is basically constant across all of the possible fitted values that you have. Again, you want to be able to see that the distribution over all of the residuals is essentially going to be normal. This is going to be helpful for you to do inference on later on, which is kind of what we're wanting to do. We want to get a new patient's BMI and make a new prediction for this new patient when we deploy this super simple model. And there's no extreme multi-collinearity, so features aren't perfect linear combinations of each other, right? So these data points are all somewhat different from one another. So there's no major leakage. These features and outcome measures are sensible. So right now we don't have to deal with any difference in scales like we talked about in a recent module. We only have one value, BMI, so I don't have to do Z-scaling or anything like that, but it's something that you might often have to consider doing. In this particular example, things seem somewhat linear. The residuals and fitted values mostly seem like a scattered random distribution around 0. It's kind of wide, like I mentioned, but it's not too bad. Homoscedasticity, so when you look through this distribution, the variance seems to be more or less maintained. It's not like a tapering off or a widening of variance at any point, so that's good. The normality of residuals here, so again, looking at the distribution of the residuals more or less follows a normal distribution. So far so good, and there doesn't appear to be any collinearity because there's no other variable to make it multi. There's no like a second variable that is totally redundant with another one. So all good. There's no major leakage. I mean, we haven't really we don't have a situation in which we can have leakage, like we talked about in previous modules with like training set and test sets, or labels into the inputs. Like we dealt with that in previous modules. There doesn't seem to be any leakage happening here, which is always a primary concern, and we don't need to scale. So.